with the introduction and all.
Okay, sure, noted on that, Gaurav. So give me 1 second. I'll go ahead and share my screen to you. So hello everyone, I am Bharat here, and I will be your host for today. And we will be having conversation here related to an F5 networks training. A small introduction about me. I have 8+ years of experience across the industry, IT industry domain. I have worked with respect to data center networking, enterprise security, application delivery controllers, and also with the content delivery network appliance as well, which is Cloudflare Akamai. And with respect to application delivery controllers, I hold a hands-on experience with F5s and Citrix. And under routing and switching, Cisco switches, Cisco routing switching appliances, layer 3, layer 2. So that was a small introduction about me. And now we'll move forward with respect to F5s. So when it comes for F5 networks, we have, if we are looking forward for an F5 network certification track, we need to get started with F5 101 fundamentals, which is termed as application delivery fundamentals exam. And this exam comprises of total of 80 multiple choice question. You'll get 80 MCQs and it's 90 minutes long. And for this is 90 minutes long for English speaking countries, and you'll get additional 30 minutes for non-native English speaking countries. And this is the first step for you to go ahead with an F5 certified F5CA, F5 certified administrator. So, and the second level of exam, we term it as F5 201, which is an TMOS administration exam. And this exam also comprises of 80 MCQs, and similar to that, 90 minutes of English speaking countries, and additional 30 minutes, which means total of 120 minutes for the non-native English speaking countries. And for you to get through this examinations, you should be at least scoring 70%. And you F5 101 exam will open door for you for 2 levels. You can either go for 201, which is the TMOS administration, or you can go for 202, which is F5 sales certification. So these are the 2 certifications. But for both of these 2 certifications, you need to ensure that you are clearing F5 101 examination, which is the mandatory one. Okay, so we'll talk about the other details of booking the examinations in the later sessions when we progress. And this particular examinations are based on F5 version 13.1. The 13.1 is basically an F5 TMOS version. It's an operating system of F5, which is built or based on Linux host. Linux is the base version. Linux kernel is the base version, and F5 have got its own custom software, which they term it as traffic management. The expansion for TMOS system is traffic management operating system. So this is the custom F5 operating system, and it is the examinations will be based on version 13.1. Current version running, the current version F5, the latest F5 version is version 17. You will be able to find that on the F5 networks websites. So, and going forward about the exam blueprint of F5 101, you will have the basics of networking, complete basic of networking, which have got VLANs and also switching, sorry, and also a basic routing table, which is static routes, and also ARP tables, and also basics of application delivery controller as well. F5 ADC basics is also required for you to have some idea about, for you to get through the F5 101 examination. Okay. Any questions related to this? Please let me know. Gaurav, do we have any questions over the chat?
Not yet.
Okay. We'll move forward with the basics of, since this course is getting splitted into two parts, which is FI 101 and 201. FI 101 comprises of network basics. We'll get started with the network basic concepts. So what I'll do is I'll just create a new computer here, and I consider that as a computer, and we can go ahead and give this as an IP address of 192.172.16.0.1, and you can consider that's the IP address, which is the layer 3 address, and you can consider the MAC address for this is A.A.A.A. Basically, MAC address comprises of 48 bits. Okay, and IP address comprises of 32 bits. Okay, so this is an IPv4 address. Now, you can barely build a network with a single computer. So I will go ahead and establish another computer here, and will give this system as an IP address of IPv4 address of 172.16.0.2, and you can give this as a MAC of b.b.b. Okay. Now, once I establish this connection between these two computers, this connection is termed as layer 1 connection. So layer 1, which is a physical layer connection. Okay. Everything will be, whenever the communication happens between these two systems, this is the bare minimum network configuration which is established between the two devices, and those two devices are communicating via a physical link, which we term it as layer 1 of an OSI model, which is a physical layer. Okay, and now as you now if we move further on the layer 2 device layer, so MAC address operates on layer 2 side of the OSI model. Layer 2 is basically, we term it as data link layer. Okay, so MAC address operates on layer 2 of the OSI model. So you might be thinking that on which layer will your network adapter or network port will operate. So this is your network adapter. Your physical links gets connected to this network adapter. So the network adapter operates on layer 1, and network adapter will have an internal ICs which gets connected to logic gates, and those logic gates will hold those MAC address, and that will operate on layer 2. So the network adapter where your physical link is terminating is operating both on layer 1 and layer 2. Okay, so that's how the layer 1 and layer 2 are interlinked. Now, what if I go ahead and connect one more device? Sorry, let me connect one more device here. I will connect this one more device and give the name as device C. You can term it as server. And under this particular server, I can give its IP address as IPv4 with an IP address of 192.116.0.3. And you can term this as a MAC address of cc.cc.cc. Okay. And now we'll go ahead and establish a switch here. You can use one switching device. I can give this, the switches are represented by an arrows. There will be a 4 arrows. Okay. So switch is represented by 4 arrows. So when the communication is initiated from 192.168.0.1, the traffic will traverse via the switch, and switch is required to build a CAM table, or you can also term it as MAC address table. Okay, content address mapping. We term this as content address mapping table. Okay. So once we get started with this content address mapping table, currently this is empty. So when the traffic is initiated from this particular device, the switch receives it on the port number 1. Switch immediately updates its mapping table with the MAC address of this device, and parallelly there will be an ARP table also gets updated, which will map this particular MAC address with this relevant IP address. So now switch knows that my source has been hitting port number 1, and I have the information, but switch doesn't have any other information about the destination network. So since this particular server is initiating the traffic to this destination server, the switch doesn't have any data about destination. It will broadcast, it will flood all the packets out of its ports where the devices are connected, but it will not flood it from where the traffic has hit the device. Basically, the traffic has been incoming from port 1. It will never send the traffic back to port 1, but rest of the ports are flooded with the IP address, with the details that what is this IP address and to whom it belongs. And as soon as the packet reaches this network or this server, this host responds back to the switch telling that, hey switch, it's it's me and I hold this particular IP address. So the switch again updates its CAM table. Okay, switch again updates its CAM table, and then it will map that Ethernet, the port number 3, this particular port number 3 belongs to this particular server, and this is the MAC address of that particular server. And it also updates the ARP table where this MAC address and this IP address are mapped. That is how the learning of CAM table happens. Okay, so this communication which happening here happens via the IP addresses. Okay, so basically this is a layer, the network layer. which corresponds here, which comes into the picture. And this IP address is termed as a logical layer, logical interface. It is not binded to your systems. It is assigned logically according to the environment where your device resides. So for this is the example for your simple local area network. So you can term this example as a LAN. Okay. So this now moving ahead in this scenario, we have looked about layer one, which is a physical layer. We have talked about layer two, which is a data link layer. We spoke about the network. We spoke about the network layer, how the communication happens. So we can have the layer three switching device as well. So layer three switching device is just a switch which can perform both layer three operation, the network layer as well, and also the layer two operation, which is the data link layer as well. Okay, so these are the bottom three layers of an OSI model, which we term it as the physical layer, the data link layer, the network layer. Now here comes, let me switch back to the presentation which I have got. So we spoke about how the OSI layers functions. So initially we spoke about physical data link and network. Then comes the fourth layer, which is a transport layer. The transport layer's work is the TCP communication works with respect to transport layer. Whenever the traffic, when the traffic is initiated from this particular system, let me go back and delete all this just to give you the more visibility. One second. Whenever the communication is initiated from this particular host towards the destination, there is an acknowledgement required to be sent that, hey, I have received the packet which you have shared to me. So that particular acknowledgement is done when we have a TCP communication in place, which we term it as transmission control protocol. Okay, so this TCP protocol ensures that for every packet which is initiated from my source host is reaching the destination. If it doesn't reaches the destination, that particular source host will not receive the acknowledgement. And if the acknowledgement is not received, the source host will retransmit the particular packet again and again until it receives the acknowledgement, or until the timeout value is hit. That there is a specific timeout value for each TCP communication. So until the timeout value is hit, this particular communication flows through the environment. So TCP works at layer 4, which is the transport layer. I am trying to transport the data. My physical connection is established. My data link layer is all set because the switching is in place. I've got an IP address in the environment. Now I need to ensure that whatever the data is being transmitted between these devices from here to here, that particular data communication is happening in a systematic manner. It's like you should not have a congestion. So that particular congestion also takes place, also addressed by this TCP device. It sends the traffic in a sequence manner, sequence one, sequence two. And if the packet size is larger than the maximum unit which can be transferred over this particular link, it will break the packet into multiple chunks prior it transport, and each chunk it will give the sequence number for that sequence, and this all packets gets reassembled at the destination site. Okay, so that now there is one more, there will be a one more protocol which works at the transport layer, which is layer 4, which we term it as UDP, user data gram protocol. Okay, so this particular user datagram protocol is uh, there is no acknowledgement required to be sent when the UDP traffic is being used. Whenever the traffic is sent with the UDP tag, or whenever the traffic is initiated with the as a UDP communication, you don't the destination don't need to send any acknowledgement. The reason for that is UDP tells you that I will transport, or I will take the traffic on the best efforts basis. My communication establishment will be on a best effort basis. It can reaches the destination, it may get lost in the between. You will have no track record of the UDP. But UDP is much more faster than TCP. The reason the source don't need to wait for the acknowledgement from the destination. It keeps on sending the traffic as long as the user is accepting it. And it doesn't matter for the source host to wait for the acknowledgement, or it doesn't care about the sequencing. It's just keep on sending the traffic. So that is user datagram protocol. Okay. And one more thing to add on here, ICMP also works at layer 4. ICMP packets also works at layer 4, which is the transport layer. So when you initiate the ping from this particular device, if you observe the first ping, you will always get as request timeout. Why you'll get first ping as request timeout is due to this particular switch is trying to learn that where the destination resides. So that learning takes place, learning, it takes a bit of time for learning to, there is a convergence time which we term that as, and that particular convergence time is causing the request timeout for the switch. And if you look, if you ping a certain server once it is in the network, you will see that the first is request timeout and subsequent pings will be successful. Okay. So all the subsequent pings, you will find it as successfully reaching. So that is the reason for the ping timeout at an initial stage. It takes a bit of time to learn and then respond back. So until now, we have taken a review on the transport, physical data link network transport. Now the session layer. What happens at session layer? Whenever the traffic is initiated, this particular traffic initiation will establish a session between the source and destination. So that's the task of session layer, to ensure that there is a single channel establishes between the communicating host, and the traffic is traversing, or traffic is flowing within that particular single session channel. Okay, so that's the simple way to explain about the session table, the session. And now if we move ahead with the presentation layer, this particular presentation layer ensures the encryption and decryption of the traffic. All the encapsulation, all the encryptions and decryption happens at session layer, presentation layer, sorry. And the application layer. The application layer, if I take an example of this particular device, I'll open up a new paint. This is my host, and this is a different cloud, which you can term it as an internet cloud. And this internet cloud is establishing the communication. This host is establishing the communication with this internet cloud. You can term this as any www.networkings.com. Networkings.com. Okay, so you will have the browser here. You can term this as a Chrome browser. Your Chrome browser will give you the interface to establish the session with this particular networkings. And that particular interface will be your HTTP or HTTPS. So these protocols works at application layer, and this application layer, this particular Chrome will provide the framework to use the application layer protocols for the successful session establishing. That's the purpose of an application layer. That's what was all about the OSI model. The fourth to first layer are a part of transport side, where all the networking related things takes place, and application presentation and session are basically the layers which works on an application side of the environment. Okay, so are we good until here? Please let me know if you've got any questions. I'll be able to answer any. Now we'll move to the TCP IP model of the environment. The TCP IP model was developed on the top of OSI layer, where, let me switch back to the paint. You have got you've got 7 layers as app, presentation, session, transport, and network, and DLL, data link, and physical. This is a part of your OSI model. The TCP IP model, your application layer gets integrated with the presentation and session. So on a TCP IP model, you will not have 7 layers. You will just have 4 layers. 2 of these layers, which are on the top, gets integrated with the application layer itself. And we will have a transport layer as a transport layer itself. And the network layer is getting converted into internet layer. Network layer has been renamed as internet layer, and the physical and data link layer are renamed as network access layer. So this is the latest TCP IP model, which is being used across all the environments. And that's how the integrations are done. The physical layer and DLL layer have been merged as one, as network access. The network layer will perform the internet layer will perform the similar function as a network layer. The transport layer remains same with TCP, UDP, and the ICMP. The application layer has been integrated inbuilt with presentation and sessions layers, which will perform the relevant operations of the relevant layers of layer 6 and layer 5. Okay, so that's what the OSI That's what the TCP IP model has been developed. And that is TCP IP model is widely used across the World Wide Web, which is www. Most of the ISPs, MPLS networks uses TCP IP models itself. Okay. So let me know if you've got any questions with this basics of the networking. I'm sharing you this basics of networking is just to refresh and brush up the knowledge, because F5 application delivery fundamentals course includes all this as a part of your sessions and courses. So 101, 201, 201 will have complete deep dive into the F5 technology, F5 ADC technology. 101 will hold a basic knowledge about networking and basics of F5 application delivery. Okay, so and this particular Ethernet frame. So this Ethernet frame is will work on the data link layer. The frames work on data link layer. Okay, the packet works at network layer. The segments works at transport layer. So transport layer, all the any data which is being traversing via the network, if it is at a transport layer, you term it as segment. If it is at network layer, you term it as packet. If it is at data link layer, you term it as Ethernet frame. And if it is at physical side, it has been already converted into a signal or logic gates to transmit to the destination. Okay, so we'll move to, give me 1 second. Okay, yeah. So we'll move to the IPv4 addressing concepts. So the IPv4 addressing comprises of 32 bits. Okay, and it's the fixed length IP addresses, wherein you will have 2 power 34 IP address, 2 power 32 IP addresses across the whole world. So that's the limitation of the IPv4 address. That's the reason there is IPv6 has already been successfully developed, and IPv6 is already live in most of the organizations across the industry. IPv6 works at 128 128 bit masking, which means that you will also have an hexadecimal. So 0 to 9, and then A, B, C, D, E. So that's an hexadecimal value. So it's of the length of 128. So 2 power 128, which is an abundance. You can survive up to more than 60, 70 years with IPv6. So that's how IPv6 has been developed by the Internet Engineering Task Force. So 32 bits are arranged in the format of 4 bits, as we were speaking about. So 32 bits has been formatted in the 192.168.0.1. So this is an IPv4 address, and this particular IPv4 address has been divided into each of this particular dot holds 8 octets. So 8 octets, 8 octets, 8 octets, 8 octets, 8 octets into 4. So you'll get 32. And so if we convert this into the binary format, you will get, we'll be able to convert this into the binary format as 111. And once again, let me go back here. Okay, so you'll be able to assign this IP address to any host except the first and last host. first and last IP address, which means that first IP address is reserved as a network ID and last IP address is reserved as a broadcast ID. So this particular, if I give this IP address as 192.168.0.1, you can assign this IP address up to 192.168.0.254. The reason is 255th IP address is reserved as the broadcast IP, and 192.168.0.0 is reserved as the network ID. So that's the concept of IPv4 addressing. And we have got 5 types of IP addresses. Basically, I can term that as not types. It should be called as classes. 5 classes of IP address. So we term it as class A. We've got class B. We've got class C. We have got class D and class E. So class A IP address starts from 0 to 126. The class B IP address starts from 128 to 191. The class C IP address starts from 192 to 223. The class D IP address starts from 224 to 239. And class E from 240 to 255. So, and if you're wondering that where exactly 127 has gone, 127 is reserved for 127.0.0 to 120, sorry, 127.255.255.255 is reserved as a loopback IP address. Loopback IP address. Okay. So if you would like to check the availability of your network adapter, you can just go ahead and on the command prompt and just try to ping 127.0.0.1. So if you're getting response, that means your network adapter is healthy state. It has no issues. So that's the reason 127 is reserved as a loopback IP address. And this all IP addresses are divided into all the classes based on their subnet masking. Okay. So prior going to subnet masking, I'll just also share you that what are the IP addresses which are not routed on the internet. So basically we term them as the private IP addresses. So from class A, we have got 10.0.0 to 10.255.255.255. So this is the segment which is private and non-routable on internet. And all these particular IP addresses are used within the LAN environment. You cannot LAN environment of your organization, of your home networks. You cannot use this particular IP address and route it across the internet. Okay. That's from class A. From class B, you will get 172.16.0.0 to 172.31.255.255. So this is for class B. And if you're looking forward for class C, the class C IP, a private IP range starts from 192.168.0.0 to 192.168.0.255.255. So all these 3 classes have their ranges of private IP address segment, non-routable IP address segment over the internet. Okay. And this particular class D is used for multicasting. So what exactly multicasting is, it will come into the picture when you have got the routing updates within the router. Once we step into routing and switch routing technologies, the multicasting will come into picture, wherein to send out an updates of any routing protocol between the routers, they use multicasting to perform that. So just for an example, for OSPF, there will, once the router gets an update for routing protocol, the multicast, the router uses multicast to update that to its peer neighbor, and that particular multicast IP address is 224.0.0.6. Okay, so for that, that's the purpose of multicasting. So it's not used over the it's not used within our own environment, but it's used as a multicast. So basically multicast is like many to many. You can, all your TVs, all your internet appliances, they use multicast to provide the data forwarding. Okay, and this is reserved pool, reserved by this is a completely a reserved pool. You're not allowed to use anything. It's reserved for research purpose by NASA, by ISRO, everything. So it's the reserve pool. So that's the concept of IP addresses. Now, what makes this IP addresses as into the classes? So that's where the subnet masks come into picture. Okay, and under this IP addresses as well, we have got class full IP address and classless IP address. The only difference between class full and classless IP addresses, when the when we have got classless IP addressing, the routing protocols will send the update to the peer by using with their subnet mask as well. Nor they'll also send the IP address, and the subnet mask is advertised across the whole particular network. With respect to classful, it's just the IP address. No, there will be a concept of subnet mask, but the advertisement will not happen of subnet mask. The subnet mask is just the standard one. Okay, so that's the classless and classful IP addressing, IP addressing concepts. So any questions here? So once we move ahead with subnet masking, the class A subnet masking will commit as 255.0.0.0. So this particular 255 is one octet. So you term this as /8. That's the first octet. In this particular first octet, you have got the network ID will remain same throughout the environment, and you are providing 3 octets for host purpose. That's the reason we have class /8 here. And if we move ahead with class B, you will reserve 2 octets for your network ID, and that 2 octets will take your class B subnet mask to /16. And when you move forward with class C, you will reserve first 3 octets for your network ID. That will make the value of the subnet mask as /24. The subnet masks are required because you need to ensure that you are not wasting the IP addresses more than the required host. If you have just got 10 hosts in your environment, then you can use the class C IP addresses, via which you will be able to allocate more networks within that environment, limiting the host's value. Okay. And if you have got more than 1 lakh hosts, then you can use /8 subnet mask, wherein you will have all your intranet within the single environment, and that particular single environment intranet will have the value within the single LAN, and all will be into the same environment, same network. If you are giving /24 into that particular 1 lakh host, you need to have a different, your environment will not be in a single LAN. They will be broken into multiple LANs, for which you need to again spend on your infrastructure, by a router, by a switch, so to perform all kinds of routing. So that's the purpose of this particular subnet mask, and you can allocate it according to your requirements. Okay, so any questions? Gaurav, are we good to stop?
We can continue for another 10-15 minutes. I think the people is watching on YouTube.
Yeah, okay, sure, we'll take it forward with the next points. I hope you are able to see my screen again.
Yes.
Okay, so we'll move to the next concept of switching and routing. So as I was sharing you the details on the paint previously, that how switching works. So this is my particular device. This is my second device. This is my second device, and I have got a router here, or you can consider this as a switch as well. I'll make the details other way. So I've got this particular connectivity between the devices, and what if I need to, if I go ahead with the switching concept, we this whole environment is into a single broadcast domain. So one broadcast domain, I can reach out to this particular device as well. I will be allowed to reach out to this particular device as well. Because the IP addresses of these devices belongs to same network, and switch is a single broadcast domain. If I just give them the IP addresses, so the switch is a single broadcast domain, 192.168.0.3. So okay, once we this particular setup, we can have it if you have got just 1 or 2 or 10 computers. Still it's fine for you to put this way of establishing the communication between your host with one switch and 3 hosts connected to each of the switch ports. What if you have got thousands of computer connected? So this setup is not scalable when you connect thousands of computer within the environment, and you want each computer to be a part of separate department. That's where the concepts of VLAN come into the picture. So I'll just go ahead and make a new paint again, and what I'll do is, once again, what I'll do is I'll take one switch here. I'll I'll take one system here, second system, third system, fourth system. All of these systems are connected to this particular switch on port 1, 2, 3, 1, 2, 3, and port 4. Okay, so and each of each of this system has got an IP address of 192.168.0.1, 192.168.0.2, 192.168.0.3, and 192.168.0.4. So all of this particular appliances have been assigned with their relevant IP addresses. What if I want the host which are connected on switch 3 and the host which are connected on switch 4 to be a different isolated domain? I don't want them to have a conversation with the device which are connected on port 1 and port 2. So that's where I can take this particular environment and make it as a VLAN, which we term it as virtual LAN. In short, we tell it as VLAN, and I'll give them as VLAN 10. So physically they are connected to a same switch, but virtually they are separated. This will create two different broadcast domain within the single switch. Okay, so I will just make this as a different broadcast domain. We'll give this as VLAN 20. We'll give this as VLAN 20. So now when the switch starts learning, or when the switch is turned on, and when the traffic is initiated from 192.168.0.1 towards 192.168.0.3, the switch will not flood traffic to the port 3 and 4. It will only flood out the traffic to port number 2, asking that, hey, this particular MAC, where do you reside? So if I give this as MAC AA, I'll give them as MAC B, I'll give this as MAC CCC, I'll give this as MAC DDD. So when this particular switch is trying to build its own CAM table, where it is starting as a fresh new one, it will not, once I separate this environment, this particular switch will not flood or will not trouble the devices connected on port 3 and 4 with the packets, asking that, do you hold this particular MAC, or it will forward directly, it will flood only to the port number 2. And once this port number 2 this device responds, it adds that particular MAC address into its CAM table, and that CAM table will be automatically updated with the details, and the ARP table as well. This will also have an ARP table updates as well also performed. Okay, now, so this is where I am splitting the host into the two broadcast domains: broadcast domain 1, broadcast domain 2. Now, what if I want to extend this VLAN? Okay, I will go ahead. I'll have one more switch. I have a different location, or my ports in this particular switch have got exhausted. I've got more new PCs getting connected into the environment. For that, I need to extend this particular VLAN to this different switch. So what I can do is I can have a communication established here. These are again 4 devices which are newly added on port 1, port 2, one, 2, 3, 3, and port 4 of the switches. Okay, so now What if I tell you I am assigning 192.168.0.4 5 here, and then 192.168.0.6 here, and then 192.168.0.7 here, and then 192.168.0.8 here. Okay, so, and again, I am building a VLAN for this and mentioning this as VLAN 10 and this as VLAN 20. So do you think that I will be able to communicate from this device through this device which is residing here on a different switch now? If your answer is yes, I will tell you that no, you cannot establish the communication between this VLAN 10 device residing here in a different switch and VLAN 10 device here residing in a different switch. For this, you need to have an uplink connected. For this, you need to have an uplink connected here with to the VLAN with the two switches. So you can take two uplinks for two different VLANs. Okay. Now, what I can do is VLANs are always tagged on the switch side on the port. Computers will not have any way to tag the VLAN. VLANs are always on the switch level, tagged on the connected port where your systems are connected. So I can do this and have a VLAN 10 passed for one link, have a VLAN 20 passed on another link. So this way I will be able to communicate between the two different switches over the two different VLAN. Okay, but let me tell you one thing. This is not scalable. This is not the way you will be able to scale when you have got more than hundreds, thousands of VLAN when you are in an enterprise level. Okay, so you cannot have multiple uplinks between the two switches in this format. You cannot pass hundreds VLAN and connect 100 ports as just an uplink between the two switches. So for this, we can have just a single link. Sorry. For this, we can just have a single link between these two switches, and we can pass VLAN 10 and 20 and many other VLANs which are residing in the environment. Many other more, whatever the VLAN, it can be 1,000, 100, 200, many other VLANs, you can pass it with this single link. And this particular concept is called as trunk. And this trunk terminology is only used in Cisco. If you are a Cisco engineer or if you have gone through the Cisco courses, you will use the terminology as trunk. For other vendors such as F5 or Arista or Junipers, they use it as tagged VLAN. So this is for F5 uses it as tagged VLAN. So don't confuse yourself. Both the functionalities are same. It's just the terminology which the vendors use are different. So it's for Junipers as well. They use it as tag. For Palo Alto also it use Palo Alto firewalls. They use it as tags. Okay, so these terminologies are different, but the functionality of these terminologies are same. Whenever the Ethernet frame is being initiated or passed from this device using this switch, and it is hitting a different switch, the switch will open up the Ethernet frame and it will check that what is the value of tag within that Ethernet frame. And once it checks the tag value, it will send out the traffic out of the relevant port where they find that VLAN is tagged. Okay, so that's how it works. So please don't confuse yourself between trunk and tag. Both are one and the same. The Cisco uses it, they term it as trunk. You might have, if you are a Cisco guy, you might have come across the port configuration on the Cisco switch as switch port mode trunk. So, and they both uses 802.1q as the format for trunking or tagging their interfaces. So, and on the F5 networks, you will find it as, on the F5 devices, you will find it as port number. There will be a port number such as 1.1, and you'll find it as tag. You will have a VLAN 10 or VLAN 20 tag and the tag ID. That's how the FI ports are configured. And they'll all will be configured with the 802.1q trunk. So any questions till here?
No, Bharat.
Okay. So 1 second.
Yeah, I think now we can stop the session.